we're here to talk about IPv6. And, this is one of those things that I've personally been exposed to for, my first exposure to it was in my MCSE training back in the 90s when I was getting certified in Microsoft Server NT 4.0, which is really, really old. And back then, it was one of those technologies that people were like, yeah, it's coming and you got to get ready for it. And so that was over 25 years ago. And what's interesting is the landscape has changed. And it hasn't changed massively, but it has changed and it continues to change. And one of the reasons why I wanted to do this event was specifically because of a meeting that I personally had. And I had a meeting with a government entity, and they're like, yeah, my network guys. So network guys that run the network for their environment, they're like, yeah, we need a crash course on IPv6. And their needs are greater than what we can get into today. And I know that a lot of people out there really need a refresher. And so this is going to be more or less a refresher for some of you with some added things to it. And I'll tell you what, I've learned and had to learn IPv6 for... I probably had to relearn it like 8 times. And it's just one of those things that, it's a little bit funky. And so we're going to talk about IPv6 today so that we have a bit more confidence when it becomes important to our success, whether it's our job success or certification success or just our curiosity, because this is a very curious protocol. And it has a lot of massively powerful things about it. Before we get into the weeds, I do want to just make sure that we know what an IPv6 address looks like, because, hey, my guess is that not all of you have really taken the time to even crack these open. So, just my anticipation of our audience. These are 128 bits long, so that means they're 4 times the length. That gives us a big number space. We're not going to get into the size of the number space in terms of how many things, but this is what an address looks like. Okay, so there's a lot of noise on the screen. Let's focus in on what an IPv6 address looks like. Okay, so there's some characteristics. Okay, so you can expect it to be 32 hexadecimal characters. You can see that there are hex characters here. So you're going to see letters A through F, F being representative of 15, which is in a 4-bit space where all 4 ones are set to, or all 4 bits are set to 1. And so you can see here, we've got conglomeration of 32 hexadecimal characters. But in the wild, this is really not how it's going to be represented, because we're going to see that there's going to be a lot of shortening. Shortening not in terms of transfats, but shortening in terms of dropping out some of the zeros that we don't need. And there's no escaping the fact that these addresses are kind of lengthy, and it does make it a little bit of a pain to work with. So let's look in the wild. We are going to spend as much time as possible in the wild in a demonstration environment, because this is really where we're going to be exposed to the reality. And it'll help us go, yeah, this isn't just theory, this is applied theory. Oh, and by the way, I want to take you on a little bit of a journey of the present state, okay? So just so we're clear, in terms of readiness out there, this is a map of the transition and support for IPv6 globally, okay? And so we can see here that some nations have been maybe slower to move over. I'm going to go over to Greenland. They're not really super IPv6 capable over there. I think it's actually interesting that this graphic at least shows that Russia is not nearly as capable. I think that's really, really intriguing. Whereas some nations have made the switch, and there are government mandates. I live in the United States, and there are government mandates that indicate, hey, we've got to have our network systems support IPv6. And so we are still in a transition phase for the rollout of IPv6 and the support of it. And just so we're clear, the current school of thought for IPv6 is we're not going to shut down IPv4. It is the replacement, but it's going to be a replacement that coexists. It essentially allows us to extend the life of the very scarce commodity that is IPv4 addresses. And if you want to know one of the biggest motivators for supporting IPv6 is the cost of public IPv4 addresses, which costs a measurable amount of money. Okay, so when you buy them to run public servers and things like that, you can expect a measurable dollar amount, about like $50, $60, if my memory serves, per year. And imagine if you had to do that 100,000 times because you're a carrier, a phone carrier. That's a lot of money. Okay, so we did start handing out. I'm going to take you to IANA, which is the big numbers authority here. And this is when they started getting handed out. So you're going to see global addresses around 2001. And so what's interesting is you might not have a need right now to worry about IPv6. It's like maybe not an immediate need. That's actually my expectation. Only a few of us are in a place where there's an immediate need for us to understand IPv6. Okay. However, that likely will change in a year, 2, 3, 4, sometime in the next 5 years. You're going to actually really need to know it. Okay, is my guess. And so we actually have IPv6 in a lot of the United States. I have it in my broadband connections to my house, whether I wanted it or not. You probably have it even if you're not using it. So it's coming in from your service provider. That's my guess, because we do really well support it. Unless you're like in a, you're off of a mom and pop shop ISP in a rural area, you probably have IPv6 to your home. Okay, that's just the guess. Okay, so let's go over to a device. And there's a lot to unpack in IPv6 that's going to help us out. Okay, so the first thing I want to show you is a router, and I just meant to do brief. So I'm going to do show IPv6 interface brief. Now, let's say you're not like a Cisco person. That's fine, okay? Because we're not really going to be super focused on Cisco. We're focused on the IPv6 addresses that we can see hanging off of our devices, okay? So the first thing I'd like you to see here is that we have two different interfaces, or two different IPv6 addresses that are going to exist on a lot of our interfaces. Okay, so this is actually not unusual. This is to be expected. And we can break down the IPv6 address so we're understanding how to read it. Okay, so what did we say? It's 128 bits and it's 32 hexadecimal characters. There are some formats that allow us to drop zeros. Okay, and the form is we can drop leading zeros in any of these things that we casually call a quartet. A quartet is 4, right? If you see a performance of a quartet, I think the Beatles were a quartet, right? Ringo, George Harrison, Paul McCartney, and John Lennon, quartet. Okay, it's 4. So what happens if there's a 0 that starts in that quartet? We don't have to represent it. And so you can see one of those quartets has just a 1. So it's actually fully 0001, okay? We can also see that there's a double colon, okay? There's a double colon, and that allows us to represent 1 to 1 through 16 different quartets. Sorry, 1 through 8 quartets. So you can actually represent all of the quartets with double colon. So it can just be 1 quartet, or it can be 7 quartets, or even 8 quartets. So JP says, is there a reason to move to IPv6 within a private network if you don't use many IPv4 addresses? The answer is, in my opinion, no. Okay, in my opinion, no. IPv4 is going to be something that, say you're a small, medium-sized business or organization, and you don't need to make that leap, then don't, okay? It's actually really a bad idea to make the leap when you don't need to, because you're probably not going to be putting the time and energy to secure it properly. And it is a whole new network suite. And it doesn't have inherent security flaws, but it does mean you're actually extending your surface area for an attack, okay? And usually we want to reduce that. And there's more things that can go wrong. And let's say you hire somebody to join your IT staff. You're going to have to skill them up on IPv6, whereas you don't have that challenge in an IPv4 environment nearly to the same degree. Okay, so we see here 2 different addresses. If you see FE80, there is an important decode. Now, here's the deal. I have seen IPv6 since the 90s, right? I've had to teach it loads and loads of times. And there's some things that are really unexciting, okay? But they're the things that are the most important. The least exciting aspects of IPv6 are the most important, because believe it or not, building a routed infrastructure is easy. Building OSPF to run on top of IPv6 is super easy. And I'm not trying to say, oh, it's easy for me. No, it's not the hard part. The hard part is actually understanding what the heck is going on. So this address that I'm highlighting here is what is called a link local address. And there's not really a good equivalent of this in IPv4. Now, you could say, oh, it's equivalent to the APIPA address. The APIPA address of IPv4 169.254, it's like a self-assigned address. But we never used it really for anything. So this is kind of in some ways similar, but in some ways very dissimilar. Okay, so what is this thing called link local? A link local address is it's a self-assigned address. Okay, that's number one. So nobody gave me this address. Okay. Secondarily, it is there for local communication. So it allows me to communicate with anything else on what is called the link. Now, the term of link is tricky because it is the equivalent of a subnet ID. Okay? Now, let's go back to our slides for a moment, and let's talk about subnets and subnet masks. Okay. So if I'm thinking about IPv4, like my assumption is, you know IPv4 decently. You've seen subnet masks and things like that. And it would be unusual to come in to an IPv6 presentation without some knowledge of IPv4. Okay, so the subnet mask and IPv4, we've kind of gotten used to it. Now, what's interesting about IPv6 is it's actually simpler. And we're going to talk about subnetting a little bit in this session, not in terms of the math, but what you can expect. Concrete expectations on what you can expect. Let's talk about IPv4 for a moment. You don't have the ability to predict what subnet mask a site is using. Like, they might be using a /24 in IPv4, but you know what? They might have chosen something else. In IPv6, the subnet mask they're going to use for any LAN segment is going to be a /64. I'm telling you that, /64. And what that means is you have one side of the address, the left-hand side tells you what network you're a part of, what is called the link. Okay, and then you have the interface ID. Now, I'll slip up from time to time, and I'll call it a host portion, because that's what we would have called it in IPv4. But the technical term, and technicalities matter here, is interface ID. So the interface ID is the latter 64 bits, okay? And there are a lot of interesting things that happen in this latter 64 bits, okay, in the interface ID. And you do need to know interface ID just because if you read documentation, which you will have to read documentation on IPv6. The latter 64 bits here we can see the interface ID, okay, is 1. And left-hand side, you see the shortened address. So this is the 128 bits in all of its glory, okay, with some shortening. You've got the double colon substitution rule, and some tests are going to test you on that. And I say some tests are going to test you on it. And by the way, I have used ChatGPT to great length to do things like summarize IPv6 RFCs, and that really, really does help, okay? Really absolutely helps. Okay, now let's talk at a high level on how this actually is probably going to happen for you as a site administrator in an organization. And let's say you're not a site administrator. Let's say you're running IPv6 at home. This will describe any pocket of an IPv6 enabled environment that is going to be connected to the internet using what we call a global address. Now, I want to take you back for a moment. You see this 2001? We're going to talk about really two big flavors of address types. The ones that start off with 2001 or sometimes 26 something, those are global addresses, meaning they're public. They're the equivalent of public. So let me take you back for a moment to that IANA document, okay? So when you see 2001, that's global unicast. Okay, that's the right term for a public IPv6 address, global unicast, okay? And so chances are you either at home, to your home, or you're to your site, you probably have like 2001. And I've also seen, I've personally seen 2620, I think it was. So you'll see something like that. That means you've got a global address, okay? And, you know, if you get curious, you could even plug in a protocol analyzer to your link to your service provider. And this is the kind of address that I see even on my cable broadband at home. Okay, so global addresses like 2001, 2600, those are routable addresses. IPv4 is routable, right? We have a network portion and a host portion. That makes it a routable address. Now, the challenge with IPv4 is we don't have consistency on the subnet masks. And right now you see two different subnet masks. Now, it's represented in prefix notation. Okay, so we still use prefix notation. But here's the deal. When you assign, let's say you have a LAN segment. And this LAN segment maybe has some servers, or maybe it has your clients. Maybe you're doing this on a service like a carrier provider, the subnets for your cell phones, the clients that, you know, that use your carrier network, that get an IPv6 address. We're going to see the deployed subnet mask of /64. Now, I'm emphasizing this because this was a big question mark for me for a really long time. Which subnet mask do we use? And what's the consistency? This is the big one that we're going to actually, when we assign an interface an address. This is what we're going to do. Let's go to a demonstration environment just so you see what this looks like. Okay. So subnet masks, they absolutely matter. And so let's look at I'll just do a show IPv6 route. So we start to see what subnet masks look like. Okay. So here, let's find a good one. I can see that I've got an entry in my routing table that would be for a global unicast address, and it's got a /64 mask. Okay? It's got a /64 mask. And here's the deal. You could do pretty much anything you want. Like, there's nothing stopping you from choosing a different mask, except for following conventions and standards for IPv6. So I could absolutely have done something funky, and I do strange things all the time, but this is not a place where you play. You don't play here, okay? If you are deploying, you're not going to be doing like a /48 to get creative, or a /96 to get creative. There used to be a standard for that. That was deprecated. So this is one of those things where you can actually find some solace and some comfort in the fact that there's consistency. Now, there are a few other masks that matter, like a /127 and 128. We'll talk about those. But this mask basically says this is standard. I'm expecting like a few different hosts hanging off, maybe hundreds, maybe thousands, although you wouldn't expect that. It supports it, okay? And let me go and let's just look. I'll just do a show run, and let's look at one of our interfaces. Just want you to see what address assignment looks like. And okay, so we see here that I don't even have an address manually configured. Wow, that's weird. That's super weird. But you know what? We're gonna see how this works. We're actually inheriting the subnet mask from our provider. We're inheriting the subnet mask that we have on this interface. So we can be told the subnet mask of our interface. Let's find one where it's actually manually configured. Okay, so I'm going to go here, and I'm going to look at my interfaces. And then let's look at my interface configuration for this one, for fast Ethernet 0/1/0. Okay. So when you configure, this is kind of what we would expect to see. If we're manually configuring, putting in the /64 mask. Okay. Now there's some other magic that you can see here, and we're going to talk about that. Whether it's good or not is up to you. We're going to see that there's some security ramifications of even small little choices that you've been taught about this. So MM says, you mentioned thousands of devices are possible. What's the relationship of IPv6 addresses and segmentation? Okay, so there's really, for all practical purposes, for all intents and purposes, there's no limitation to the number of hosts you could actually numerically address on a single subnet, okay? So in terms of segmentation, let's talk about the term of segmentation, because that's part of the question. In this case, segment is in the context of a broadcast domain, which means a subnet, okay? And so you can have 2 to the 64th power number of unique addresses 2 to the 64th power is a lot, okay? It's more than the entire IPv4 address space, okay? However, in production, you would still follow the typical rule of thumb, not putting more than around 250-ish clients on a network. Now, you might get up to 500 or 1,000, maybe even a little bit more, but it would be super messy to put more than, I'm going to say, super conceivable max, just from a communication standpoint, probably around 2,000 to 4,000. Okay, and I wouldn't go that far. Okay, now here's what some places do. In terms of segmentation, segmentation is putting people in a unique pocket. Okay, so in a production environment, a segment could be like, hey, I'm going to separate sales from marketing. That's segmentation. We do that with VLANs. But in the extreme case, what we call microsegmentation, everybody gets their own subnet. Okay, so that's the reality. Okay, there's RFC like 9099. Okay, RFC 9099 specifically talks about IPv6 segmentation and a lot of other things too. And I think I'm remembering the RFC number right. But anyways, standard practice for IPv6, if you really want to go to the extreme, is enforcing principle of least privilege, or enforcing microsegmentation is an important thing. Why is that? And it's actually zero trust architecture. Being in part of the same subnet as somebody else, you inherently trust some aspects of the communication. Zero trust architecture is a principle of security that is important in IPv6. It's also important in IPv4. And one of the expressions of that is to put like a server in its own subnet, which is a little bit crazy to me. But that is the modern practice for segmentation. Sorry, went on a little bit of a tear there, but that's segmentation. So you could have, it would be not unusual to have 200, just like you would have for IPv4. So the same rules kind of apply, okay? Yeah, 9099. Okay, good. Got it right. All right. So let's keep on trucking here. I want to revisit that link local. This is where I don't want to lose you because it's uninteresting. Here's the deal. If you need to know IPv6, you need to know link local addresses. Okay? And BC Scott says segmentation is automatically defined. No. Segmentation is something you manually enforce, and it's something you manually enforce by controlling the deployed subnets. Okay, so I'm gonna give you a simple way to think about this. Let's say you have 20 servers. Put them all on the same subnet. You're not segmenting the servers from the other servers. So if they're all in the same, you have not segmented that. But maybe you've got 4 different types of servers in that. So maybe you build 4 different subnets. I'm going to put my web servers in this subnet, and maybe my VoIP servers in this subnet, file servers in another. So that would be segmentation. And then you take it to extreme. Let's say every server gets their own subnet. You could do that too. It would burn more addresses. Okay. But that would be more secure because people would have a harder time hopping from server to server. So that's how you think about it. Hopefully that helps. Okay. Link local addresses. Everybody gets these. Windows clients running IPv6. Your network infrastructure running IPv6, you get them. And it's how they talk to each other. So if you've heard and been trained, hey, these are like a PIPA, nobody uses a PIPA in IPv4, but everybody has to use this, okay? So it's a self-assigned address. We choose it. It's literally pulled out of thin air, okay? Now, it's pulled out of thin air, but we do test and make sure We do a duplicate address detection so we can be sure it's not going to collide and there's not somebody else who pulled out the exact same number in thin air. So it happens. Like, theoretically, it's mathematically possible that two stations could come up with the same link local address, but they'll detect it with duplicate address detection. Now, why this is important is if you're troubleshooting any of these environments, you're going to see some communication that you're not going to understand what the heck is going on. Okay. So here's where you're going to see it. You're going to see it for almost any of the network services that happen inside of IPv6 are going to use these. And you look at over here, ICMPv6. Okay, wait, let's pause for a moment. What's ICMP? Internet Control Message Protocol does things like echoes and echo replies, so it's used in ping. It's used in some other things too for IPv4. But they add functionality, the key functionality that builds the connectivity on a LAN is done with these link local addresses. Okay, so look at this. Just look at it and we can infer something interesting. Router solicitation. So I want you to think about Ethernet LANs for a moment. Ethernet LANs, when you come online, you get an address via DHCP probably, right? For IPv4. DHCP. You're going to learn your default gateway from DHCP. How do you learn adjacent routers in a subnet for IPv6? This is the primary way it goes. So instead of being reliant on DHCP, which still can get used, but it's kind of a little altered, you're going to learn about what your router is. And by learning your router, you're going to know what subnet you're a part of. Let's see this. Okay. So I'm going to go back to our branch router. And I want you to see something. I don't have an assigned IP address that I manually configured, right? I don't. But I have an address. I absolutely have an address. Show IPv6 in brief. I've got an address. How did I get the address? Well, it's probably something to do with this. Specifically, that something is ICMP. One of the flavors of ICMP, or one of the capabilities of ICMP, is router advertisements. I can solicit for a router. Okay, so let's actually see this. And by the way, this is a key component of IPv6. It's not like one of those, like, hey, this is hyper advanced and you're only going to use it in a few places. Nope, it's one of the underlying things. It's how even a Windows host can get its router. So let me go in. Oh, and what we're going to do is we're going to debug this, okay? And let's do neighbor discovery and address. Okay, so I turned on 2 different debugs. I'm probably going to get more than I need, but I don't want to have to do this like multiple times. Okay, so I am going to remove that I'm going to remove this. I'm actually going to say no IPv6 address. Probably going to get yelled at. That's not what I'm trying to have you look at, even though you can see a little bit of like ICMP neighbor discovery there. It's because I basically deleted the thing that had been learned from ICMP. Okay. So let me go in and I'm going to turn that back on and we're going to watch. Okay, so there's a lot of spam here. Turn off the debugging, and then we'll see. We're going to see there's this thing. Let me see if I can see the call out. Received a router advertisement. Okay. I received a router advertisement. And what that router advertisement did is it told me what the prefix was. Now, what a prefix is the subnet. So look here. I learned my subnet ID. I learned that I am to be using this specific mask. Okay. Oh, and Josh is asking about EUI64. We're going to talk about that. We're going to actually talk about why, like, traditional operating systems and you shouldn't use them anymore. Okay. So I will get to that. Okay. So this is part of the story now. This is how we learn what subnet exists. So a client could learn which subnet it's a part of, just like when it's using DHCP for IPv4. So a client wants to know what subnet am I part of. Here, ICMP does it instead of DHCP. So that's totally, totally different, okay? The other part of this is clients are also going to use ICMP for ARP functionality. Now, I said ARP. Oh, there's no ARP. Now, this is also not super exciting. I'm going to put myself on the left-hand side. ARP functionality is replaced entirely in IPv6. ARP was broadcast-based, but what did it do for us in IPv4? It helped us figure out the MAC address of something we want to talk to on our subnet. Okay, so when you think about how does your client get to its router? Well, it learns of the IP address by DHCP and IPv4. Here in IPv6, it learns of its router's address via router advertisements. But how does it know the MAC address to talk to? If you're going to talk on Ethernet, you need to know its MAC address. So ICMP v6 specifically does neighbor solicitation. Neighbor solicitation triggers a multicast communication. Okay, triggers multicast communication, and it says, hey, who owns this MAC address? So instead of running ARP in IPv6, we run ICMP v6. Okay, so let's go back out. This it's not all that glorious, but it's super important. Okay, so I'm going to do show IPv6 neighbors. Okay, I'm going to do show IPv6 neighbors. And I am also going to turn on a debug. Okay, so what this is it says, hey, I'm going to tell you the MAC address of that thing you're trying to talk to. Okay, there's going to be a little bit of noise. We're not going to talk about that until we do a ping. Okay, so this helps us understand layer 2. In the same way that ARP tells us a MAC address, now that is taken on by ICMP v6. Okay, now let's do something. Let's ping something. Okay, so I'm going to look at my routing table again. let's look at our routing table. Let's ping something, okay? So let's find a global address that's out there. And this was learned via OSPF. Now the config for OSPF, specifically OSPF v3, it's not all that interesting. It's not all that interesting. It's not so not interesting. I'm just going to show it to you. So the config for OSPF is commands that say, hey, I want to turn it on for an interface. The command to turn it on for an interface is IPOSPF1, and this is the full config that I have. So it's not all that, it's not big, okay? So I'm just plugged in to OSPF, but I've learned about this address right here, okay? Via OSPF. So we can see that it's specifying, and this used to be really concerning to me. It used to be concerning that it's kind of hanging out. Like the double colon says what happens beyond this is 0. Okay? So but that's okay. It just means we have 4 more quartets of 0 because this is a prefix. This is a subnet ID. Okay? So that's okay. We're not expecting another address. And then it says 64. Yeah. Unless we're doing some manual summarization inside of OSPF, that's how we're going to come. The administrative distance, if you happen to be like a Cisco person, that's the same administrative distance of the IPv4 version of OSPF. And it's 3 gigabit links away from me, so it's actually assigned a cost of 3. It's not actually a hop count, although it functionally works out the same way. So let's ping this, okay? I want to ping this, and the interface ID of the device that I want to ping, I think, is 1. So let's just ping that. Okay, got there. Okay, I was able to get there. Now notice that generated a lot of other things. Why? Because we just reconfirmed what was learned via that ICMP protocol. We can see that I pinged successfully through a few different layer 3 devices. Built, we just basically slapped on OSPF. This is not an OSPF discussion, but we use that to build the connected infrastructure for these environments or for these devices, okay? And you know what? Those same tools that you're used to, ping and traceroute, they all work. Let's do a traceroute there too. I'm going to do a traceroute. Oh, I highlighted. That's not what I meant to do. Okay. Boom. So ping, traceroute, here's the thing. A lot of the things you learn in IPv4 translate with effort. It's not like always a one-to-one translation, but sometimes it is. Ping and traceroute, those are the tools that you know and love. Okay, we don't have to lose those. Okay, they're still super useful as they were in IPv4. Okay, so when we need to know the MAC address of something, we're going to do ICMPv6 neighbor solicitation. Neighbor sounds weird, okay? So if you hear neighbor solicitation, neighborship happens a lot with like routing protocols. This is not a routing protocol thing. This says I'm building adjacencies with other things in my IPv6 subnet, okay? In my IPv6 subnet, okay? So we already talked about the router discovery stuff here, so I'm going to move through this. One of the things in the discussion that is super cool to talk about is that EUI64 discussion, okay? So let me jump there, okay? Just jump. Wasn't going to be my talking point in this order, but it came up in the chat. Okay. Now, EUI64, I remember learning this back when it was introduced to me in like the early 2000s. Okay. Here's something that's really interesting about IPv6. Okay. I want you to think about IPv4 for a moment. And I want you to think about things like ping sweeps. Okay. Ping sweeps. So a ping sweep is a tool that allows for somebody to discover the IP addresses alive on a subnet. Okay. A ping sweep is a lot harder to successfully run in IPv6. Okay. I want you to think about that. Imagine doing a ping sweep when your subnet mask is /64. If you've ever done a ping sweep, you would think, oh, I might have to wait a little bit. But if you have to wait to do a sweep of all of the addresses, I mean, it's going to take you a while and you're going to get discovered. Okay. Now, that's one security benefit of IPv6, is the fact that the subnets are so large, guesstimation of the IPv6 addresses is hard. Okay. There's more to the discussion than that. The other part of the discussion is we do want to avoid giving up information about ourselves. Okay? I want us to all agree about something. You don't want to give information about yourself to somebody else unless it's absolutely required. Like, for instance, if I ask you, hey, what is your street address? You wouldn't give it to me, right? That's information. It's not like really revealing, but it's information you wouldn't want to give out. Now, there's this feature of IPv6 called EUI64. And what it does is this. It says, I am going to use my MAC address to self-assign the interface ID. Now, remember, interface ID is just the host portion, okay? Interface ID is just the host portion. So we can see that we have the interface IDs being tucked away here. And they're actually the MAC addresses, okay? I want you to look at the MAC address above. So here you see the MAC address of this Intel card, 0, blah, 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 3B8E. You can see that MAC address was copied into the IPv6 address. And it was copied in by way of EUI64. Now, what I didn't know until, well after I learned this is you shouldn't use this. You shouldn't use it. Why? Because you're revealing what kind of equipment you have. Imagine this. Imagine you've got a firewall and you're self-assigning yourself an address using your MAC address. Well, like say it's Palo Alto firewall. You just told somebody, hey, I'm running a Palo Alto firewall. And then somebody's like, well, I'm going to enumerate that. Okay? So this is an address type that we actually still teach, but we shouldn't use it. Why? Because we're going to give away too much information about ourselves. And in that discussion, let's just keep the discussion going. Here's the modern practice for addressing ourselves. So it was actually mentioned in the chat, hey, we don't use this anymore in operating systems. And for a while, I didn't understand why. Okay? For a while, I didn't understand why. But it's because, hey, we don't want to embed our MAC addresses. And so this is a pretty good representation of the what to expect from a modern operating system, okay? So what we expect from a modern operating system is you're going to get probably a stable address, okay? You're going to get a stable address, one that is consistent. Okay, but let's talk about security for a moment, okay? On the internet, there are bad actors. We know that, right? If you keep using the same address, let's just say you are someone that people want to attack, or you're a system that somebody wants to attack, and you always use that same address when communicating on the internet, that leaves you open to attack. Okay? It absolutely leaves you open to attack. So this is how security conscious we are in IPv6. So instead what we do, we also add on temporary IPv6 addresses. If you're surfing the web, this is what you want to do. If you're using the internet, this is what you're going to do. Okay? So the stable one, yeah, the stable one, you might need that stability for like DNS tracking and things like that. Maybe you have a service that people need to hit. But for client-facing things, you can have any legitimate IP address in the IPv6 subnet, and that's where you're going to see these, okay? So you're going to see these temporary addresses. Now, what's interesting about these is they are the temporary addresses. You basically, it's like rolling the dice, but it puts it through a mathematical algorithm to make the interface ID, remember that's the latter 64 bits, that means that these are not reversible and they're temporary. So now let's say your traffic, let's say you're always on the internet doing something and you're somebody we want to attack. Let's say it's like maybe a government official or a journalist. They do get attacked, they get hacked and things like that. So it'll be hard to figure out who's doing what. This is a really, really beautiful thing. And notice I'm calling out some RFCs, not so you know them, but if you are learning about IPv6 and you have to do that work, you are going to have to look at the RFCs. I resisted it for just such a long time. Now, there's one more important thing that I want to share with you today, and it goes to something that I skipped over, but I wish I had been told this. Okay, I wish I'd been told this. Okay, how are we going to do this in the real world in terms of just addresses? Okay, now I did say that we're going to apply a /64. Okay, but what is your site going to get? Okay, and if you happen to get these, by the way, some of you know this. Okay, you might have had it been communicated from your service provider. You might have discovered it. Might be part of your documentation. What prefixes are you getting coming from your ISP? Okay, it's not unusual to get these. Okay, now if you're just at home, it's very possible you're just going to get a 64. But if you have a business grade fiber optic link, using it just for any old IPv4 connectivity, probably get a /48 or a /56. Okay, so let's just park on 48 for a moment. You think to yourself, hey, I've seen the term subnet. How does that actually really work? How do we do the practice of subnetting? First, yes, we still have subnetting, but it's different. Okay. The act of subnetting, whether it's IPv4 or IPv6, is the act of extending the starting mask that you got. Now, it might sound like an oversimplification, but that is what it is. Subnetting says, I'm going to add the length of the subnet mask, and by doing so, it gives me additional number spaces to work inside of. Okay, so this is really cool. So /48 to 64. Okay, focus on that. Here's the scoop. your site, you might have like just a branch office that got a /48. You probably have this. You're probably not even using it. So what this says is, let's just say this is what's assigned to you. And you can even learn this because there's actually a DHCP process that happens in a lot of these cases that assigns a prefix to your site. But ultimately, we have a /48 that comes in. Now, what does that mean we can do? It means we can build 65,536 subnets here. 65,000 subnets for just a site. Now, if you happen to get a /56, you can only have 256 subnets. How am I, like, where does these numbers come from? The amount of subnets that you create is 2 to the power of borrowed bits, 2 to the power of bits that you add. So 2 to the 16th power. And how can we know this with certainty? How can we be okay with this? Be like, yeah, this is a concrete thing. Because of the consistency of the fact that we're going to be using /64s for most of our subnets. We're going to be using /64 for most of our subnets. Okay? And I mean the vast majority of them. Okay? So, yeah, if we get to borrow bits, and I know that I'm borrowing up to 64 consistently, you get to basically borrow everything to 64. That's the standard. So instead of being creative, we no longer have to be creative. Like, one of the challenges with IPv4 subnetting is it's an act of creation. You got to be creative. In this case, you just, borrow however many that takes me to 64. So theoretically, you could even get like a /60 at a site. You still have 4 bits to borrow. Okay. So that's how subnetting acts, so you can use it internally. Now, here's the gory details, okay? You're going to be deploying /64s. That's what I already shared with that. There used to be a standard /96. It's deprecated. That's one of the challenges of IPv6, is the fact that so many good ideas died on the vine. They died on the vine because they were a good idea that had some flaws, okay? So there's another mask here, /126. Technically, that would give you 4 addresses to work with. It's not favored, okay? And by the way, if you do IPv6, you're going to want to at least have things like this follow the expected. You don't break the mold, at least in terms of your number system. So here are the 3 masks you're going to use, okay? You're going to use these 3. Okay, so 64 for any of your broadcast segments. And then you theoretically could use a 64 between 2 routers, okay? They can actually get by with link local addresses, so they don't need an address. But if you did need to give them global addresses, you would use a 127, which means they can have 2 available interface IDs inside of that. So for a really long time, I've read so many books, and they just don't tell you, like, what do you actually do? This is what you actually do. 64 is for your subnets, for your LANs. 127 is legit for point-to-point. It's still, this is like right now, 2024, this is what you would expect. You don't do a 126. Maybe you read it in an old book. That's old. It's deprecated. And then if you're building a loopback address, and we build loopback addresses so that we can, give an extra address to something, maybe for management purposes, 128 would be the mask, okay? So in the real world, those are the masks that you're going to have. This goes over the subnetting again, just for expectations. So you might actually, you could call up your service provider and say, hey, what's my IPv6 addressing space? You could do that if you're like the site administrator and you already work with their techs. They could tell you these things. I'm not saying to then go out and deploy it. because if you deploy it, you have to secure it, okay? But you're probably getting a /48 or /56 to your site, okay? And believe it or not, you probably have at least a /64 to your home. So IPv6 is not something that is out there for the future, okay? It's a right here and now sort of thing.